Ever pondered on how the digital devices that we use daily, from our computers to smartphones, all function? What is this invisible force that drives them? It's digital logic, an integral part of electrical engineering and computer science, focusing on the design and implementation of digital circuits. Imagine digital circuits as an intricate network of roads, where the cars are discrete voltage levels, typically represented as zeros and ones. These circuits perform logical operations and process information, forming the backbone of all digital systems. At the heart of these circuits are logic gates, the building blocks of the digital world. They carry out basic logical functions like AND, OR, NOT, NAND, NOR, XOR, and XNOR. When combined, these gates can create more complex logical functions, much like how individual bricks can form a towering skyscraper. Now, how do we analyze and design these digital circuits? That's where Boolean algebra comes in. This mathematical framework involves operations such as AND, OR, and NOT, which mirror logical operations. It's the architect's blueprint for constructing our digital skyscraper. All this talk of zeros and ones brings us to the binary number system. This system, which uses only two digits, 0 and 1, is pivotal for encoding and processing data in digital circuits. It's the language that our digital devices understand and communicate in. But where do these binary numbers get stored? Enter flip-flops and latches, the storage elements in digital circuits. They store binary information, much like how a locker stores your belongings. Alongside them are registers, groups of flip-flops that temporarily store binary data during processing. And then there are memory units, the digital equivalent of a library, storing and retrieving data. You might recognize some of them: RAM or random access memory, and ROM or read-only memory. For channeling multiple input signals into a single output, we have multiplexers. Imagine them as a busy traffic cop, directing multiple lanes of traffic into a single lane. Demultiplexers, on the other hand, do the reverse, splitting a single input into multiple outputs. They're indispensable for data routing and selection in digital circuits. And what about the arithmetic and logic operations? That's the job of the arithmetic logic unit, or ALU. It's a digital circuit that performs operations like addition, subtraction, AND, OR, and others. It's a vital component of a computer's central processing unit, or CPU. In the world of digital circuits, there are two main types: combinational and sequential logic circuits. Combinational logic circuits generate output solely based on their current input values, like a vending machine dispensing a drink based on your selection. Sequential logic circuits, however, remember their previous state, as well as the current inputs. It's like a lock that needs the right sequence of numbers to open. So, how do we design these digital circuits? That's done using hardware description languages like Verilog or VHDL, or through graphical tools like logic gates on a schematic diagram. In summary, digital logic is the invisible force that powers our digital devices. It's composed of logic gates, Boolean algebra, the binary system, flip-flops, latches, registers, memory, multiplexers, demultiplexers, the ALU, and combinational and sequential logic circuits. It's an intricate network of roads directing and processing the flow of data in the form of zeros and ones. It's the backbone, the architect's blueprint, the language, the storage locker, the traffic cop, the vending machine, the lock, and the design tools for our digital world. It's a fascinating world, isn't it?